礼拜一大家所教的习题，阮教授跟安教授跟我讨论了一下子，我比较了一下子，大概你们的情形，比起我在 Stonebrook 教过2次大一物理，我觉得满意，就是大家对于做习题的态度跟习题的成绩都很好。所以这个很好。现在又有了一些新的网上，比如说是 Syllabus 3，可是这 Syllabus 3啊是有一个图，这个图是讲说是一个projectile， the trajectory of a projectile。你们对于这个图有没有什么意见？这个图不太对，因为他画的不是一个 parabola， 这个 parabola 跟这个的有一点分别，因为 parabola 它的这个 curvature， 就是越来越一个 parabola 到下去的话，几乎就变成直线了它这个是这个是我的秘书画的，他没有把这个 parabola 这个观点放进去。我想对于一个球一个circle 的性质，跟一个 sine wave 的性质，跟一个 parabola 的性质，你们自己多画几个以后，你就知道是可以看出来是不一样的。今天我们现在先讲一个这个记住我们上一回算了一阵以后就得出来了一个公式，这个公式我现在给大家讲一下子，有一个方法可以比较简单的记住。因为那人所做的一件事情是有一个 r， 这个 r 把它变成那个 derivative 就变成什么状态呢？就变成2个，一个是 r dot， 还有一个呢是 r theta dot。你如果看你那个上回我们试算的时候，从 r 这个 vector 变成它的 derivative 以后，就变成2个 component， 一个是在原来的方向，可是的 magnitude 是 r dot， 一个是在90度是 r theta dot， 所以就记住了一个 r， 你要变成它的 time derivative 的时候要变成2项。好，那我把这个叫做1，把这个叫做2。我来把这个1的 derivative 同样的做一下子，就是拿这个1当作是这个 r， 仿效刚才的办法。那它的 derivative 很显然是什么呢？是要分成2个，一个呢是 r dot 再 dot 一下，所以就变成 r double dot， 还有一个呢是这个 r dot 转90度乘上一个 theta dot， 所以变成这样。我就是照抄从 r 变成这2个，现在不是 r 了，是 r dot， 那当然就得是这样。这个是这一部分的。那么另外那部分呢，我也如法炮制。另外本来是 r theta dot， 所以它的这个 derivative 呢， 就是 r theta dot 的 dot。因为刚才说一个东西的 dot， 在它原来的方向呢是它那个东西的 magnitude 的 dot， 所以就是这个。可是还要有一个是它转90度乘上 theta dot， 所以就变成这个。所以这就是 r theta dot 再乘上 theta dot， 所以就变成4项，这2项这2项，那我把它加起来，那你看在这个 r 方向的是哪个呢？是 r double dot， 是从这儿来的，跟这个负的 r theta dot square。在这个 theta 的方向呢，也是2个，这是 r dot theta dot 加上 r theta dot 再 dot 一下，是这等于OK， 底下我们做一个非常简单的例子，就是一个秋千swing。假如这个叫 theta， 那么there's a swing which swings back and forth. If we analyze the force on this swing, there's one force which is mg going downwards. There's another force which is along the direction of the rope. 绳子的是这个方向。But the sum of these two has to be along the direction of the tangent, because if you take this formula, r double dot,我们先看 r dot 是等于0， because the swing is confined to move on a circle, therefore r double dot is equal to 0。那你把它踢进去的话呢，这项等于0，所以等于所以等于 r hat 乘上 minus r theta dot squared 加上 theta hat r dot 是 0， 这个是 r theta double dot， right？ 所以 therefore 它的 acceleration 有2个方向，一个是在 r 的方向，一个是在 theta 的方向。那么它的 force 呢是在这个方向，这2个加起来是在这个方向。所以我如果把这个 force 拿来的话呢，这 force 有一个 component 是 r 的方向，一个 component 是 theta， 是 theta 的方向。 this component balances the component of the tension. So this is the component. So therefore, we get the force m 乘上这个 acceleration r theta double dot. That's equal to the component of mg. This is theta times the sine theta. 而是负的。Therefore, theta double dot is equal to minus g sine theta. Over r. 这个你如果把它写成这样，它变成这样。This is called a differential equation. 微分方程。 微分方程 is a very important subject in differential and integral calculus. You'll be learning about differential equations in your mathematics course. We shall come back to this formula. To solve a differential equation is called to integrate it. And there are several ways of integrating it, but we'll come to that in the future. I think we better do some exercises. Chapter 5, problem 47p. It talks about a monkey on a pulley, and the monkey is climbing up, and this pulley has a weight of 15 kilograms on the other side. The monkey weighs 10 kilograms. So it's a very simple. Let's analyze what are the forces on the monkey. There's one force which is going downwards. That's its mass. Let's call this capital M and this small m. So there's a small mg. There's a force on monkey. And the other force is the tension on the rope. The monkey is climbing up. If the monkey doesn't do anything, he will accelerate upwards because the 15 kilograms is heavier than its own weight. But if it starts to climb very fast, it could go the other way. So if we take T minus mg, that's the total force on on the monkey. This, according to Newton's second law, is equal to ma, where a is the acceleration of the monkey upwards. So the acceleration is equal to this. But we know what t is. Now we do it on the block. On the block, there is a force which is mg, and there is a tension of t. So t minus mg is equal to the acceleration upwards of the big mass, but that's equal to ma minus, because the monkey's acceleration upwards is equal to the block's acceleration downwards, because they are on the same string. So we have these two formulas. With these two formulas, you can solve this problem. For example, what would be the case if a is equal to 0? If there's no acceleration, that means if a is equal to 0, that means t has to equal to mg. If t is equal to mg, if t is equal to, what happens if a is equal to 0? Then from this formula, t is equal to mg. But t is equal to I've made a mistake, just a minute. Does anybody understand where I've made a mistake? First, this formula. No. The mistake is that the monkey's acceleration is not the string's acceleration. So, this is the monkey's acceleration. And this is the string's acceleration. But if the monkey's acceleration is equal to 0, in other words, the monkey doesn't go upward or downward with any acceleration, then t is equal to mg. And we then get this formula for how the string moves. The string moves like the heavy mass. If the acceleration mass, suppose this big mass is not moving, then t is equal to mg. If t is equal to mg, then capital Mg minus small mg is equal to MAM. So in that case, M minus mg is equal to ma of the monkey. So the monkey's acceleration is equal to m minus m divided by m times g. In other words, for the monkey to climb such that the big block does not move, the monkey has to be accelerated like this. Let's try the next one. The next one is a block. A block moving on a, let me see. A block is moving on a surface without tension. So on the block, there are the following forces. This is T, the tension on the rope, and this is the mg. The problem is what is if the acceleration, the block begins to move in this direction. So ax is equal to 0.12 meters per second. And the mass is equal to 9,500 kilograms. The block does not move, this angle is equal to 18 degrees. The block has two forces on it, T and mg. T can be decomposed into a vertical component and a horizontal component. The vertical component of T must balance mg, because if it does not balance mg, that block would either move upwards or move downwards, which it cannot. So we therefore know T times sine theta, sine 18 degrees, has equal to mg. So that tells us what T is. And then the acceleration, T cosine 18 degrees, is the horizontal force. And that horizontal force has to be equal to the mass times the acceleration. So if I take the ratio of these two, I get tangent of 18 degrees is equal to g over a. Or A is equal to G times cotangent 18 degrees. Let's try another one. there's a block on a frictionless slope. It suffers a force R. When you have two surfaces in contact, if there's no friction, then the force between the two is always a normal force, always perpendicular to the surface. 所以一个 force 是 R 是 perpendicular to 这个。另外这个 block suffer 一个 force 是 mg。在这个题目里头说是它的 acceleration 等于 0， 而且告诉你说它的 mass 是等于100个 kilogram。然后他说还有一个第三个 force， 第三个 force 是这样。所以呢 since the total acceleration is equal to 0, so the total force is equal to 0. The net force is equal to 0. So R plus mg 这个对积是向下的 plus F has to equal to 0. 假如我把这个this angle is given to be 30 degrees. Then 我们现在把 it's most convenient because two forces are along the x and y direction, so it's best to resolve R into horizontal and vertical component. So R, this is a minus R cosine theta has to be equal to mg. R sine theta has to equal to F. Because R cosine theta is a force upwards which balances mg. R sine theta balances F. So if I take the ratio again, I get tangent theta is equal to F over mg. So F is equal to mg times tangent theta. Theta is equal to 30 degrees. There are a lot of exercises in chapter 5. I recommend that beyond doing the exercises that I assign, 你们另外再做一些 exercise. 你做多了这个 exercise, 每一个 exercise 其实都很简单。底下我讲chapter 6。chapter 6主要是讲 friction。为什么会有 friction? Why is there friction? When you have two surfaces in contact, now each surface consists of many atoms In fact, many layers of atoms， 一层一层的atom。在一个，比如我的手、我的皮肤 ，the atoms are not necessarily very regularly arranged， 不一定是很规则的。But in a crystal, it is very regularly arranged. However, in a usual crystal, there is usually a foam. There's a surface layer above it, and on that surface layer, it's not necessarily very regular. 可是 if you have a very clean crystal surface, if you have another very clean crystal surface of the same type and cut the same way, if you put the two together, it is very possible that it almost matches. If that is the case, the friction is extremely large, because the frictional force between two surfaces is usually the sum of the forces of all the atoms along one surface exerting on the atoms on the other surface. If it is a perfect crystal, then these two forces are extremely large. And in that's not what the usual friction is about. That's much, much larger than a usual crystal, than a usual friction. In fact, if you have two of those things like together, you cannot separate them. It's just, but that's very rare, because first, you don't have two perfect surfaces. Second, they may not match. So in a usual case, like my hand, it has all kinds of irregularities. And if I take the table also has irregularities. And when I put my hand on the table, there are areas where they exert great force on each other, but there are areas where they are not exerting great force. And that's the science of friction. It is an extremely messy subject, because it depends on the condition of the surface. In recent years, surface physics has become very important, but one does not study such things like the interaction between my hand and the table. That's a very messy subject. It is one talks about more accurate surfaces, because surface interaction is very important for manufacturing. You should read page 100 of the book, because it gives you some more detailed discussions about the interaction between two surfaces. So the usual discussion of daily life's friction is a phenomenological description. Phenomenological. Phenomenon means 现象。Phenomenological means 现象的。So the usual study of friction in daily life is a phenomenological study, and you cannot do very deep studies. So it's mostly empirical. Empirical means 经验的，是一个经验的 study。那么这里头就产生了一些 concept， 一个叫 static friction force。static 的静止的 friction。这个静止的 friction 叫 static。一个 static friction force 通常是这样，这个不是一个很准确的东西，是比如说有一个 block 在这儿， 那么这个 block 跟这 surface 间有一个 normal 的 force， 所以这个 block suffer 一个 force 是 n 向上。That's the force on the block by the surface. Of course, according to Newton's third law, the block also exerts a force minus n on the surface. So let's first talk about the force on the block. That's equal to n. That part is always there. But there is also a frictional force. Suppose the block wants to move in this direction. Then the surface exerts a force F static against it. For example, if the block is on a slope, there is a gravitational force which makes it slide. But there is a frictional force, Fs, which suppose there's a block here. There's a gravitational force. Part of the gravitational force is balanced by a reaction this way. But part of the gravitational force exerts a force this way to make it slide. Then the friction is Fs, which makes it, which balances that part and makes it not move. So that's called static frictional force. The static frictional force experimentally is equal to a static coefficient times the normal. So in this case, because the block does not suffer, does not have any tendency to move, so this Fs is equal to 0. But in this case, this Fs is not equal to 0. This Fs balances the gravitational force pull downwards. This is if the block does not move, if there's no relative motion between the two. There is a kinetic frictional force. For example, this block, if the block moves either upwards or downwards, then the force, then the frictional force, which is parallel to the surface, is not governed by this. It's governed by a different coefficient. So this is a coefficient of friction for static force. This is a coefficient for friction for a dynamic force, for a kinetic force. Mu s is usually less than mu static. And you have that experience. If you have a block on the surface, so suppose I put a heavy block on the surface. If I try to push it, if I push it very gently, it doesn't move. Why? Because there is a opposing frictional force exerted by the surface on the block which balances my push. But if I push very hard, it will begin to move. Why? Because when the frictional force is larger, the force that I push is larger than this frictional force. This static frictional force has an n. N is the weight of the block. If I push too hard and exceeds this number, then it will begin to move. After it begins to move, it obeys this formula. But this formula, the mu k, is usually smaller than mu s. As a consequence, once it starts to move, the frictional force becomes suddenly less. This, in fact, you have the experience. If there's a very heavy object here, you can push very hard. But once it starts to move, it suddenly becomes easier. Read page 101. Let's do sample problem. 6-1. This is on page 101. It talks about a particle which has an original velocity on a frictional surface, so it becomes slower and slower till eventually it stops. V final is equal to 0. The coefficient of kinetic friction is given to be 0.6, and the distance is 290 meters. The question is, what is the original velocity? For a physics problem, the way to do it, the easiest way, is you first collect a few formula without putting numbers into it. So we know V0. Suppose the time interval between here and here is t. Then there's an acceleration, so V0 is equal to AT. And the distance is equal to 1/2 AT squared. And we also know the force on it is equal to MA. And MA is equal to M times the normal force. The force is equal to mg times mu k. This is a kinetic case. So we have three formulas. Out of these three formula, we get, for example, G is equal to mu kg is equal to A, and T is equal to square root of 2x over A. So it's equal to square root of 2x over mu kg. V0 is equal to A times T is equal to mkg times T. So as I told you last time, it's best to first not put numbers in, just collect the formulas, and after you get eventually a formula where the right hand side all consists of known quantities, at that point you put in the numbers and first check that the dimension is correct, then do the computation. Another topic is called drag force. Read chapter, read section 6-3. Drag force means if you have an object moving, for example, in air, a body moving in a liquid or in gas, then there is a frictional force on it, and that's called drag force. That's an extremely complicated subject. It's related to what is called hydrodynamics.流体力学. 流体力学 is an extremely important subject because if you want to design a good car, you have to deal with the friction. If you want to design a submarine, you have to deal with friction. And this is a complicated subject which is half theoretical, half experimental. Actually, the fundamental equations of hydrodynamics, at least for liquid, was already studied in the 18th and 19th century because of practical use. But there are improvements of the theory and of the experiment, and it is a very important subject. And it is important both from the theoretical viewpoint and from the application viewpoint. Now, there are some somewhat tricky problems in the book. Let's do chapter 6, 27p. It talks about a block resting on a slab. So this is a small block with a mass of 10 kilograms. This is a big slab with a mass of 40 kilograms. You can think of imagine there's a surface. This surface is frictionless, no friction. And it's given that the static coefficient of friction is 0.6. The kinetic friction is 0.4. And the block, the small mass, is given a big force of 100 newtons. The question is what happens to the block and to the slab. Now you have to think, it's like there's ice underneath, and there's a big block on top. On top of the big block, there's a small block. All these coefficients are between the big block and the block and the slab, but between the slab and the small block. There's no friction on the bottom surface. It's like on ice. Okay, imagine, suppose you have such a thing. You have a heavy object on the ice, and you put a smaller object on top of it. Now you give the small object a big push, 100 kilograms, 100 normals, 100 Newton. So let us first assume there are two possibilities. One is that the block and the slab would move together, would slide together on the ice without relative motion between the two. 另外一个呢，是 the block would the small mass would move, and the 你可以猜想，那个 slab 也 move， 不过那 slab move 的没有这上面那个大，就是上面那个 move 带着底下那个。这个到底是什么呢？我们得要试一下子。所以我们第一个 let's assume no relative motion. Between small and big mass. No relative motion between small and big masses, between the block and the slab. 会发生什么现象？ In that case, you think of the two as together. So its total mass is 50 kilograms. What is the force on the total force? 当你说 total force 永远是 external force, total external force on the two. 有两个，一个是 the force by the surface on it, which has to be 50 kilograms in order to balance the gravitational force. If it doesn't balance, the two would fly up or down. Of course, that's ridiculous. But there is also there's no horizontal component because there's no friction. So the only force is 100 kilograms, 100 Newton. So the 100 Newton is equal to the total mass times acceleration. The total mass is 50 kilograms times acceleration. So therefore we know the acceleration is 2 meters per second squared. In other words, if the two move together, then we know the acceleration. The acceleration is 2 units, 2 meters per second squared. Now we consider the force on the block, on the small mass. So the small mass now moves with an acceleration of 2 units. And so now we consider force on the small block, on the block. It has one force which is 100 newtons. It has another force which is the friction. If the two move together, that does not mean that there's no force between them. There's a force between them. And we know the acceleration. So therefore, this force on the block has equal to 10 kilograms times acceleration times 2. But the force on the block is equal to 100 newtons minus the frictional force. Therefore, you can calculate the frictional force. This is therefore equal to 20 newtons. So therefore the force is equal to 80 newtons. That cannot be, because the normal force between the bar block and the slab is the weight, which is 10 kilograms. That 10 kilograms multiplied by static by 0.6 is only 6 newtons. Pardon? So therefore it's not possible. So what we have done is we analyzed, could it be that the two move together? The answer is not possible. It's not possible because that requires too large a force, frictional force between the two. Therefore, 所以现在就是 therefore there's relative motion between the two blocks, between the two masses. Once 你知道它有 relative motion， 你就知道它的 friction. So the friction F between the two 是等于什么呢？是等于它的 mass， 等于是这个小的 block 的 mass 是10个 kilogram。乘上它的 mu kinetic， 所以是等于10个 kilogram 乘上0.4，等于4个 kilogram。sorry， 4个 Newton。Pardon？ 我没懂，你反对我讲这句话，说是它的 frictional force 是等于4个 Newton。我没懂你们，这 frictional force。
别人在说40，就是还有一个 g， 重力加速度 mg。
sorry， 等于 sorry 10个 kilogram 乘上 g 乘上0.4，这个 whatever 这 value 是，这差不多是40个 Newton。等我想刚才我是不是也弄错了？咱们走回去一下。你等一下，是100个 Newton 等于50的时候 ，A 等于2个 meter。
最后一行就60。
对，这差不多是40个 Newton。如果我们知道了这个，我们现在就算它是40个 Newton。假如是这个 friction。这个 force between the two， 我们现在知道是40个 Newton， 那我们再来 analyze 一下子这个 small mass 的 acceleration 是等于100个 Newton 减去40个 Newton divided by 10个 milligram。10个 kilogram， 这是 6个 meters per second。这个我应该画成这样。而这个 acceleration of 这个 small of the big mass， 在这个 big mass 上的这个 force 呢是40个 kilogram， 40个 newton， 40个 newton divided by 40个 kilogram， 所以等于1个 meters per second。What that means is that if you give the small block a very large force, it would begin to slide on the big mass. But when it slides, it exerts a force on the big mass, and therefore the big mass also moves, but at a slower acceleration than the small mass. 假如我们把这个问题改一改 ，if however we use only 10 normal, 10 Newton on the small block,那是what happens？ 那我们就回到这个 A 的情形。Assume no relative motion between the two masses。那个时候它的 acceleration 是什么呢？是10 Newton divided by 50 kilograms， 所以这只是0.2个 meters per second square。0.2个 meter per second squared， 我们现在来算一算这个两个之间的 reaction 是什么呢？那这个 force， that's the frictional force is equal to T 10个 Newton 减掉这个 friction force。Between the two blocks is equal to 10个 kilogram times the acceleration, which is equal to 2 meters per second, to 2 Newton. So the force is equal to 8 Newton.这还是不行，这个问题得要再改，更小一点，不是10个，因为我现在要把它变成比那个要小。假如比它变小了以后，它就两个一块move了。我是不是又错了一个？
那个是60。
啊？
以前那个是60，所以它小于那个前面那个60。
刚才是68个Newton，这个现在对 ，sorry， 这个现在小于60。所以它就一块move。 no relative motion. OK， 那我看了一下子这个 Chapter 6。Chapter 6是一个很 complicated chapter because friction and hydrodynamics are very difficult subjects. But for freshman physics, we don't go into the details. So we go to the next chapter, Chapter 7. Chapter 7 discusses energy. Now this is an extremely important subject. What we are going to discuss, there is a kinetic energy, 中国叫做动能。There is a static energy. These two were understood already around Newton's time, although it may not have been called so. Or in other words, it's clear that Newton and people like Laplace, Lagrange, all knew about these kind of energies. But then, of course, people knew that there are other energies. There's electromagnetic energy. There's chemical energy. For example, there's fire. And the energy involved in fire is a chemical energy. But actually, of course, all chemical energy are electromagnetic. When you understand chemical reactions, you know they are all due to electromagnetic energy. But anyway, all this energy was successively studied and understood. And finally, in the mid-19th century, there was the concept of conservation of energy. And that's also called the first law of thermodynamics, 热力学的第一个定律。The first law of thermodynamics, perhaps it was a complicated story, but perhaps the person who made the greatest contribution of this was Lord Kelvin. The conservation of energy, or the first law of thermodynamics, is one of the fundamental laws of physics. We'll have many discussions of it. But in the first two chapters of chapter 7 and 8, we are talking about the kinetic energy and the static energy, which were the earliest known concept of energy. We shall prove later that the kinetic energy, that if a body moves with a certain velocity, it has a certain energy. And that energy, you might say, let's first define it as a kinetic energy. Why we define it, we shall come to later. And it's equal to 1/2 of mv squared. V squared, of course, is equal to when you write this, that means V dot V. It's a scalar product. And of course, because of the definition, this is, we defined V dot V as the product of the two lengths times the cosine of the angle between the two. But the angle is 0. So it's so this is equal to V squared. This is the definition of kinetic energy. And its unit is 1 joule. 1 joule is equal to 1 times kilogram times velocity squared, which is m. But you can easily show that this is equal to Newton times meter, because Newton is kilogram. Newton is equal to kilogram times m divided by s squared. So if you multiply this by meter, you get this. So Newton meter is equivalent to kilogram m over s squared, and it's called a joule. Okay, next we are going to show why this is important. We have the formula. The easy way to show this is, let us take the time derivative of the kinetic energy. That is equal to d dt of 1/2 of m v dot v. 根据我们上回曾经讲过，一个 derivative of the product of two things is equal to the derivative of alpha beta is equal to alpha beta dot is equal to alpha dot beta plus alpha beta dot. And that is true also for scalar product, because a scalar product can be written as a sum of the x component multiplied plus the y component multiplied plus z component multiplied. So you apply it to each of those three terms, you get so therefore this means that this is equal to 1/2 of m of v dot plus 1/2 of m v dot v. But scalar product is commutative, so therefore these two terms are the same, and so therefore you get m v dot which is equal to mv dot is equal to acceleration. Which is equal to the force according to Newton's second law, or is equal to force dot dx dt. you see both sides have dt, so if I multiply by dt and integrate, I get the integrate of d all I did is I multiplied the dt by both sides. And integration merely means you add together. The integration is equal to sum. Integration is actually equal to sum. Only what you're summing is very small parts. You make a continuous thing. But so this is what is in here is a continuous thing. You write a small d. That means this kinetic energy is keep on increasing, for example. And you put the increase into many small parts and then add them together. But that, of course, is nothing but the original, the final kinetic energy minus the initial kinetic energy. Let me repeat. What I said is a fundamental thing. Namely, the integral d is nothing but the sum. What is meant by a sum of many d's? Many d's means you have a increasing kinetic energy. You divide that kinetic energy into a million small steps, and you take each small increase and add them together. But if you take each small increase and add them together, of course, the final result is equal to the total difference. So therefore, you get this. Now, the last few sentences is the spirit of differential calculus and integral calculus. And that was a revolution. That's a revolution launched by Newton and Leibniz. And unfortunately, in China, that revolution was never launched and never understood. It's the most fundamental and yet the simplest concept once you understand it. But for ancient people to realize it, it took a long time. What I want you to do is you deeply appreciate this point, and you can manipulate without thinking. So the steps here, this notation of dx dt as the derivative was due to Leibniz, and it's very important because once you learn how to use it, you don't have to think. So what I did is I just multiplied dt by both sides as if dt is a number. Dt is not a number. It is a number and yet not a number because it's an infinitesimal quantity. And the subtlety of differential and integral calculus is to learn how to use this infinitesimal concept. And once you have learned to use it, once you have learned the notation, you can deal with it as if it's just a number. So I multiply both by dx, and I get this, and I get this. So this is equal to. So this expression says, if we define kinetic energy as 1/2 of mv squared, then the increase of the kinetic energy so defined is equal to a sum of f dot dx. Now f dot dx means you divide that motion into many little intervals, like a million intervals. In each small interval, you calculate the dx. That's the displacement. Multiplied by the force at that time. That's what is the meaning of this. And that is called work. F dot dx is called the work. It's an infinitesimal work because we are only talking about a small distance. So it's this total infinitesimal work. Therefore, the physical concept really is when a force moves a body, then that force does some work on that body. And that work is equal to the force times the distance. And you accumulate all those works, you get the total work. And that total work is equal to the increase of the kinetic energy. And that is the reason why this formula is important. And that is the beginning of the concept of energy. Here we only talk about the kinetic energy. The book calls this the work kinetic energy theorem. The book spent several pages discussing it because it did not use calculus. You see that using calculus is extremely simple. So all of you must learn calculus as soon as possible. Once you have learned calculus, it's much easier to understand physics. Now, we were talking about the increase of kinetic energy. But that's not the particle could be decelerated. A particle could be moving, and I'm trying to oppose it. So it gradually slows down. In that case, it's a decrease of kinetic energy. So the left side would become negative. But it is still equal to this because the force in that case is negative. So I'm doing negative energy on it, negative work on it. So we have the concept of negative work. When you talk about the work on something, it's always the force experienced by the object. That's the force. So important. F in the boxed equation. What is F? F is equal to force on the object. So if a particle is moving fast toward me and I oppose it, the force on the body is a negative. So it's a negative work on it. 这个 on 非常重要，因为 Newton's third law always force comes in pairs, and you have to remember this word on. By the way, 我刚才讲的这个是 three dimension 的。Notice the boxed equation is a three-dimensional equation. In other words, suppose a body is moving toward me. If I try to oppose it, I may also try to move it sideways. But that sideways force, that part of the force experienced by the body, it has a F, which is perpendicular to the displacement. So that force does not do work. All I'm saying is that remember that this formula, as explicitly written, is a three-dimensional formula. You take the F and dot into dx. Okay, anybody with any questions about the kinetic energy? I think we better talk about the potential energy next time. Otherwise, we'll be going much too fast. So I have no more prepared material to tell you today. By the way, I was told that for the holidays we are going to miss 2 lectures, but one of them will be replaced by a lecture on the 9th. It's on a Saturday. However, that day I have already another engagement, so I'll ask Professor Ran or Professor An to meet with you on the morning of Saturday, October the 9th. Okay, goodbye, and have a good 中秋节.